Have you ever looked at a medical scan, like an X-ray, and wondered how a computer can automatically pick out the important stuff? Like, how does it separate bones from tissue all on its own? Well, it's a huge part of medical AI. And today, we're going to break down one of the classic, most elegant ways to do it. It's called Otsu thresholding. Let's dive in.
Here's our game plan. First, we'll get a handle on what Otsu thresholding actually is. Then, we'll see how a computer turns a picture into data it can understand. After that, we'll actually apply the method, clean up our results, and then we'll do a quick wrap-up of the key ideas.
All right, so let's start with the big picture. At its core, this is all about one thing: automatically splitting an image into two groups. You got the stuff you care about, which we call the foreground, and then, well, you have everything else, the background.
Now, the end goal here is to create what's called a binary mask. Just think of it like a stencil. It's a super simple image where every single pixel is either pure black or pure white. That's it, no gray areas. The white parts are the objects we found, and the black parts are what we're ignoring. This simple mask is pretty much the starting point for almost any kind of image analysis.
And this isn't just some academic thing, by the way. This exact technique is still used all the time in real-world medicine. On a CT scan, for instance, bone and air show up very differently from soft tissue. So thresholding is a crazy fast and effective first pass to find those structures before you do anything more complicated.
So the big question is, how do you decide the exact shade of gray that's the cutoff point between what becomes black and what becomes white? Well, that's the magic of Otsu's method. It's this clever algorithm that just looks at all the pixels and automatically calculates the one perfect value to split them into two groups. No guesswork, no fiddling with sliders. The computer just finds the best split for us.
But for the computer to find that perfect split, it can't just look at the picture the way we do. It needs to see the data underneath. So how does an image get turned into numbers that a machine can actually crunch? Let's check it out.
We're going to start with this image right here. It's a public domain chest X-ray. Since it's grayscale, every pixel has a value. Think of it like a scale, from 0, which is pure black, all the way up to 255, which is pure white.
Now, our eyes are great at this. We can instantly see the bright white of the ribs and spine against the darker parts of the lungs. But how does a computer see that same difference, numerically? The answer is a histogram. This chart is actually pretty simple. It just counts how many pixels there are for each brightness level. And look at that. You can clearly see two humps in the data. That big hump on the left, that's all the darker pixels, the soft tissue and air. And that smaller spike over on the right, yep, those are the super bright pixels from the bones. So, just looking at this, where would you draw the line to split them?
Well, that's the exact question Otsu's method is designed to answer for us automatically. So let's go ahead and run the algorithm and see what number it comes up with to create our mask.
And there it is. The algorithm crunched the numbers from that histogram and decided the best possible threshold is exactly 128. That's our magic number. Any pixel darker than 128 becomes black, and any pixel brighter becomes white. Simple as that.
And if we look at our histogram again, you can see exactly why it chose that number. That red line at 128 falls perfectly in the valley, right between those two main clusters of pixels. I mean, it absolutely nailed it.
Okay, so what did that actually do to our image? On the left, we've got the original X-ray. In the middle, that's our brand new binary mask. Look how clearly the spine and ribs pop out in white. And on the right, we've overlaid the mask just to show you exactly which parts of the original got selected. That's a really powerful result from just one automatic calculation.
But if you look closely, you'll see our mask isn't quite perfect yet. There are all these little white speckles and bits of noise scattered around. It's a fantastic start, but we often need to clean this up and isolate just the main thing we're interested in. To do that, we use a cool trick called connected components. Basically, the computer scans our mask and groups together all the white pixels that are touching. This turns all those white regions into distinct objects or blobs that we can count and measure. So, after running that analysis, the computer found 153 separate objects. But just look at this table. The biggest object has an area of almost 80,000 pixels. The second biggest, it's only 754 pixels. It's pretty obvious that one of these things is not like the others. There's one object that is just way, way bigger than anything else. And we can see it right here. The algorithm has drawn boxes around the 5 largest objects it found. And that giant red box, the one labeled number 1, that's our 80,000 pixels superstar. It's clearly grabbed the main anatomy of the chest. Everything else is just noise.
So, the final step is incredibly simple. We just tell the computer to throw everything away except for that one single largest component. And look at the difference. On the left is our original noisy mask, and on the right, a beautifully clean, refined mask with just the main object we wanted. It's a perfect way to get rid of all that small, irrelevant clutter.
And there we have it. We went all the way from a grayscale photo to a clean, isolated object. So let's just do a quick run-through of the main ideas that got us here. So, we learned that a binary mask is our goal, that simple black and white image. We use the Otsu threshold to automatically find the best cutoff point without us having to do anything. Then we used connected components to find all the individual objects in our mask, which is essential for picking out one specific organ. And finally, we just kept the largest component as an easy and effective way to remove noise.
So I'll leave you with this thought. This whole process, from a photo to a clean anatomical mask, was done using a classic algorithm that's been around for decades. If something this simple can get us a result this good automatically, it really makes you wonder, doesn't it? What's going to be possible as modern AI keeps getting better and better in medicine?